All right, so in this video, we're going to be looking at solving exponential and logarithmic equations. And so we're going to go through a bunch of examples and just kind of look at the techniques that we need for them. We're not necessarily going to solve the equation all the way to a solution because we're looking for strategies to get you to a point where that you can proceed. So we have one group of problems that I refer to as eliminate the base problems. So we can use this type of technique with equations, both log and exponential equations. But the idea is that we want to match bases and then eliminate the things that we have in common. So in this first example, we have 3 to the x plus 1 equals 9 to the x. Now 9 is a power of 3, it's 3 squared. So we can rewrite that problem this side, the right side of the equation, as 3 squared to the x, which will simplify to 3 to the 2x. And now, since the bases are the same, we can drop them and just set the exponents equal to each other. And then you have a linear equation, and then you would solve from there. Another example would be 4 to the x plus 3 and 8 to the x minus 1. Now, it's harder to convert 8 to a power of 4, but we can convert both 4 and 8 to powers of 2. So 4 is 2 squared and 8 is 2 cubed. And so if we make that replacement, powers to powers, we multiply in the exponent. And so the left side of our equation would become 2 to the 2x plus 6, since we multiplied x plus 3 by 2. And on the other side of the equation, 2 to the 3x minus 3, since we multiplied x minus 3 by 3. And now we have the same base on both sides of the equation. We can drop the bases and set the exponents equal to each other, and again, solve from there. Now, we can also do the same thing with logarithmic equations if they have the same base of the log. So log base 3 of x is equal to log base 3 of 2x minus 8. When the logs are the same, you can cancel them and just set x equal to 2x minus 8. Now, anytime you're dealing with a log, once you get your solution, you have to make sure that it is defined in both of your equations. So for instance, if I were to get a negative answer here, then I would worry that log of a negative number would not be defined. So I do have to check those solutions much more carefully in log problems than in exponential problems. But the procedure is still basically the same until you get to that checkpoint. When you have the same log in the equation, but they're in different terms, what you can do is apply log properties here to combine this into a single log. So since these are added, we can put them inside the log as a multiplication. And then we have a natural log of thing equals a natural log of a thing. And we can cancel the natural logs. And then we can just set the two sides equal to each other. If I multiply the x through the x minus 1, I get x squared minus x equals 6. And from there, I have a quadratic equation, which I would then attempt to solve by putting everything on one side of the equation and factoring. Now, as I mentioned before, if you're doing log problems, you have to make sure that the solutions are valid in the original version of the equation. So just like in this previous example, if we were to get a negative answer for either of our x values, log of a negative number would not be defined, and we would have to throw it out. We would also have to verify that log of the number minus 1 is also defined. So it's the original version of the equation that we have to verify. And so for a problem like this, we do sometimes have to throw away solutions. Now, we're going to try another technique later on that you can use to also verify the number of solutions that you end up with. Now, if you have an equation that's kind of in quadratic form, these are going to look somewhat similar to our previous example, except instead of having 2 terms, one on each side of the equation, we have 3 terms in this case. And so what we're going to have to do is make a substitution. Now, 3 to the 2x is equal to 3 to the x squared. So this is how we're going to get a quadratic solution. And then 3 to the x is our middle term, that's where we're going to make our substitution. And then the 2 doesn't actually change. So since this first term is 3 to the x squared, that becomes our substitution variable squared. And the middle term is just our substitution variable minus 2. And so from here, we would then factor, and we would end up with solutions of y equals 1 and y equals minus 2. We should always double check to make sure that they work. Now, when we substitute this back into our original exponential equation, 3 to the x equals 1 is going to have a value we can solve for. But 3 to the x equals negative 2, which is the other value for our y. Exponentials without a negative in front of them are always positive, and so it's impossible for 3 to the x to equal negative 2, and so we can throw out that as a possible solution. But when 3 to the x is equal to 1, we are going to get a solution, and it's going to be x equals 0. Now, another similar kind of equation would be something like this, where instead of writing 3 to the 2x, they actually square the base. So here we have a term 6 to the x, and then 36 is the square of 6. So really, this is 6 to the 2x. For the same reason, it's 6 squared to the x, and then we multiply the exponents. So the substitution we're going to make is 6 to the x, and then this term will become the square of that, and then this term has a 6 out front, and then the 6 to the x becomes our substitution variable. The 9 doesn't change. And so again, from here, we have something we can factor. In this case, we're going to get y minus 3 squared. So y is equal to 3. And then we can set that 6x equal to 3, and then solve from there. And then this equation actually is going to look be somewhat similar, but we have to do a little bit of algebra for it. So here, because we have x plus 2 in the exponent, we might think, well, this isn't going to work. But no, we can just pull out the plus 2. 2 to the x plus 2 is 2 squared times 2 to the x, and 2 squared is 4. So we can convert it into a form that was like our previous example. This 4 is just the coefficient of our substitution. And then this component right here, 2 to the 2x, this is our substitution variable squared. And if we make our substitution for y is 2 to the x, we get y squared plus 4y minus 12. And again, we solve for a value for y. And assuming we find a positive value for y, we set that equal to 2x. We can then continue to solve for what the value of x is. If we get a negative value for y, as we're bound to do here, then one of those values will have to be discarded because a 2 to the x is never going to be negative. And then similarly, we have a problem like this. Now, here we have 3 to the x, and now we have 3 to the negative x, and it might seem like, oh dear, this isn't really like what we had before, but it actually is. What we're going to do is we're going to multiply the whole equation by 3 to the x to get it into our more familiar form. And when we do that, 3 to the x times 3 to the x is going to be 3 to the 2x. 3 to the x times 3 to the minus x is just going to be 1. And then we're going to end up 5 times 3 to the x is 3 to the x. So this is now our middle term, 5 times 3 to the x. 14 is now our constant. And so we're going to make our substitution, y equals 3 to the x. And we're going to end up with this one becoming y squared. This piece right here becoming minus 5y. And then this is our constant. And then again, from there, we would factor any positive solutions we set equal to 3x, and then we can solve from that point. We may have to take the natural log of both sides or what have you. But if we had any negative solutions equal to 3 to the x, exponentials can't be negative, and so we would throw that case out. Now, another kind of problem we could encounter are mixed bases, so exponential problems or log problems that have different bases. So for instance, e to the x plus 3 is equal to pi to the x, or 2 to the x plus 3 is equal to 5 to the x, for example. Now, we have to get the variables out of the exponents in order to solve for them. And so you can apply the log to both sides. Where the bases match, then great, you'll get some reduction going on. So here we have e, and we take the natural log of both sides. The log of e is 1, and all we'll have left is the exponent x plus 3. In the case of log of pi to the x, we can apply log properties to bring the x outside, and we now have x times a constant. Log of pi isn't a nice number, but it is a constant. And from that point, we can just go ahead and solve, collect our x terms on one side of the equation, factor out the x, and then divide both sides of the equation by that amount. And we get an ugly looking answer, but nonetheless, we do get an answer. So another similar example might be like this. And again, we've seen examples of this coming out of our quadratics. We have maybe 3 to the x equal to 6 or something like that. We would have a similar thing going on here. The first thing to do is to get the exponential component by itself. So in this problem, we would divide out the 0.3, and then we would do the log properties in order to get the variable out of the exponent. And so then it would continue more or less similar to our previous example. An example like this is actually quite similar, these financial models. Again, we would divide out the 750, and then we are trying to get at this variable in the exponent. Everything inside this parentheses is just a constant. And so this is our base. It's a weird looking base, but it's our base. We would apply the log to both sides, and then we would pull the 12t out of the exponent and then divide by log of this base, and then we would be able to proceed from there. Now, if the logs are of different bases, then we can use our change of base formula in order to get them into a form that is easier for us to work with. So log base 2 of x and log base 5 of x, we're going to rewrite log base 2 of x as log of x over log of 2, and the other side of the equation, log of x over log of 5, and then cross multiply, and so we end up with log of 5 times log of x and log of 2 times log of x, and these multipliers outside the log we can then bring, again using log properties, into the exponents, and now we have log of stuff equal log of stuff, and then we can drop the logs, and then we can proceed from there. In this case, we can factor out natural log of 2, and then we have natural log of 2 equals 0, so this has to be x to something which equals 0. It's 0, x is 0, and then in this case we would have x to the log of 5 over 2 is equal to 1, and any number that equals 1 is going to have to be a base of 1. 1 to anything is always 1. So we end up with solutions of x equals 0 or x equals 1. Now, some problems of these kind can be done algebraically, but there is one more technique that you can use for some of these really crazy problems, and that is graphing. Now, in some problems, we're just not going to be able to solve them algebraically. They either can't be done at all, or as we saw in some of these other cases, they can be done in theory, but they can't be done easily. But if you combine things like exponentials and logs, for example, or exponentials and just naked x's, then you're going to end up with situations that you can't actually solve. So here we have x squared equals a log. We can't solve that algebraically for x. Here we have e to the x equals x. Also can't solve that easily for algebraically for x. Here we've got an x in the log, and here we have an x in the base of the log. Also can't necessarily solve that easily for x. So these are all examples of things that are just algebraically going to present real challenges. So in those circumstances, then the graphical approach is the way to go. Now, if I have this example right here where I have log base 3 of something is equal to log base x of 10, what I can do is I can rewrite this as a natural log change of base formula in order to put them into my calculator. And then I can go ahead and use the intersect feature on the calculator in order to determine where they cross each other. In this case, we can see there's a value here where they cross each other. In their TI, you can use the trace function, although it may not be accurate enough. So you can't really try to read it off the graph. But you may need more decimal place accuracy than you can get out of just sort of visual inspection. But that is an alternative that the graphing approach is an alternative that you can use, assuming you don't need like 10 digits of accuracy in order to get this result. You may also be able to find it using the intersect function. The trace function tends to jump too much, so you can't just scroll along the graph in your calculator and try to get it. You do need to actually narrow in on the more exact value, and intersect will do a better job than trace will.